Thanks for the invitation.
The laptop's not actually plugged in.
I have a little subtitle, putting weighted TMDs on better footing. So a lot of this talk emphasizes the B-space formalism, where CSS formalism on TMDs is formulated. I want to point out that in the EIC white paper, okay, so last week there was, I think, emphasis on this diagram, and even up to here, I guess, right? So all of this. In the EIC white paper, there is this, I guess I would have to say, somewhat controversial statement in this map that you can start from TMDs and integrate over KT and get collinear PDFs. I'd like to explore this in the context of the CSS formalism and see if we can get a better handle on how we can interpret this. So when you do this, this all involves going into coordinate space and dealing with UV and IR divergences. There's a lot of work that's been done on this for, almost, what is it, almost 40 years. So let me also, I've saved this slide. I can't find the original talk now, so I had to take a photo of this with a piece of paper. And it's from Davidson Soper. I mean, he's not the only one who cautions one. But when you start to talk about transverse momentum-dependent parting distributions, it says if you're going into the woods, you have to be careful. There are some subtle issues and definitions of these. On an intuitive level, and in Parcon models and model building, people use this relationship. So I'd like to argue that using an enhanced version of the CSS formalism, we can make get better understanding of this relationship, if there is one that's rigorous. What we did this year was to use CSS to get a relationship between the unpolarized TMDs and the collinear PDFs at leading order. The more interesting result was that we were able, through the CSS formalism, to verify something that's been written down earlier, which is that the first moment of the Sivers function is related to the twist-3 function. So this is the paper where this is discussed. So a lot of this work relies on this modification of the W plus Y construction to match the cross-section over QT point by point from small hadronic scales to large scales in this work that was done with John, myself, Alexei, Nabu, Ted, and Bowen Wang. We are not the only ones who worked on this subject. In fact, I'm sure that I have left out more than as many people I've mentioned here. There's different formulations, there's different methodologies, and it's a kind of an ongoing subject. I think Nabu is going to talk about this a bit. Just one slide on this. What we're talking about when we do TMD factorization is in B-space, we have the TMDs and the fragmentation functions. Here I'm just speaking about unpolarized with the Y term, where the Y term is essentially allowing subtraction of the double counting that would happen if you just naively took the W term, which is this TMD contribution, the fixed order, just added it. I'm sure many of you are familiar with this. There's a lot of work on that as well. This naive connection between the TMDs that are sitting in this formula, but it is Fourier transforms, this is extremely important in our field because everybody's using it. And so we need to clarify it better if we can. And Elke had these two equations in her slide, and other people have mentioned it. So we really must confront these central issues of whether there is really a relationship between these collinear objects and TMD evolution and factorization, and in particular for polarized phenomena. So let's consider something less exotic, the unpolarized TMD and collinear PDF. Again, this equation ignores UV divergences, soft gluon radiation, and so forth. I would recommend, if anybody's interested, almost all of these works, in particular the earlier ones, discuss in some form or another what is fraught with a lot of subtlety and difficulty. Something I want to emphasize is that Werner gave a talk here in 2014 and also Transverse, where he looked at this in the context of joint resummation and comes up with a result that we find is quite similar using CSS forms. Okay, so somewhat a review of TMD factorization, which has already been gone over by Ted, but I'm going to need some of the tools. These are the main people who contributed to this. We know that the cross-section in TMD factorization breaks down into a W term and a Y term. The W term is expressed in terms of Fourier transform TMDs that depend on two scales, these two auxiliary parameters, which are arbitrary, and they're reflected in the Collinear equation for the TMD PDFs and the renormalization group equation. So, because it depends on two scales. And because a lot of this work is done in B-space, it's worthwhile to consider the cross-section Fourier transform where, so this is the W term. For the unpolarized, we used a bit different notation. It's more in line with Baqueta et al. But it's worthwhile to consider the cross-section in B-space and all of the structure functions and ask yourself the question whether these structure functions factorize. This is just a statement of kinematics at this point for SIDIS. What's nice, if they do factorize, they become a simple product convolution. So each one of those functions, if those structure functions factorize, they have TMD PDFs. And as Ted went over the other day, renormalization of these is richer. There's both UV renormalization, and then you have to deal with renormalization of the soft factors. And there are two types of divergences that appear: rapidity divergences and the collinear divergences or infrared divergences. But you must do UV renormalization. So this is our naive definition of the correlator, but this is completely on subtraction. This quantity satisfies the Collinear equation, which gives rise to essentially a derivative of the soft factor that appears as part of the factorization where the soft factor is used to separate right and left movers, so it's really necessary for full factorization of the W term. There's also the normalization group equations. So when you solve these equations, you get the evolved TMDs. So this is Ted's slide from the other day, which where he uses a capital letter for the TMD in B-space, and you can see that it's written in terms of refactorizing this piece here in terms of the OPE, where these are the coefficient functions, and these are the collinear PDFs. And herein lies maybe a connection between TMDs and collinear PDFs. This is the Sudakov exponent, which has both perturbative contribution and non-perturbative parts. We've already implemented the B-space formalism, B-star formalism, so that we separate out that which can be fit and that which can be calculated from first principles of QCD. I want to point out, though, that it's not just F1 that satisfies the Collinear equation, but it is this combination of this F1 and the Sivers function, or the Sivers first moment. Now, this Sivers first moment is essentially a derivative, a B-space derivative of the Sivers function in B-space. This formulation is also used in the lattice studies of Engelhardt and formerly Bernie Musch and others. So it's this whole correlator that obeys the Collinear equation. This was recognized earlier by Zhangbo, Mertz, and Ted, and so forth. What that means is that the Sivers function, first moment, and the unpolarized have the same evolution curve. What they have different is, of course, the non-perturbative contribution. So in its full glory, the W term now is a product of a piece that is, we call WOPE and a W non-perturbative. The OPE piece is just that part that is got the perturbative contribution and the where these TMDs here are re-expressed in terms of their OPE expansion. Okay, so this is shorthand, sorry. This is shorthand notation for what's on the next page, for the unpolarized TMD, the fragmentation function, and then for the Sivers W term, which has the Sivers first moment and fragmentation function. Okay, so we're going to be focusing on this small b limit of the piece of the W term for each TMD, and also for the Sivers function. Now, I want to point out that in 2012 and 2011, there was work done on looking at this, what is the collinear quantity here that appears in the OPE. And you can just write something down, but in fact, it's the experiment function. In fact, it was shown at next to leading order that the evolution of this quantity through the B-space formalism was established by Zhangbo, Feng, and Bowen Zhao. Okay, so I want to mention, make a note about some of the properties of this. So just look at the unpolarized here. This mu b turns out to be C over B star. When b is very small, B star just becomes B, because there's this B max that separates the perturbative and non-perturbative regions of B space. So this can become a hard scale, and it plays the role of a hard scale in the PDF. It sits here and represents the scale, and it's also in the coefficient function. If you want to go any further with exploring this relationship between the left hand and the right hand side, you encounter something that's been well known for many, many years, is that when b gets very, very small, you encounter these large logs. And so if you're performing a Fourier transform, you will encounter logs that are unphysical, because the W term is not supposed to be extended to small b, because it is well outside its design region. So you can understand this by simply looking at the Sudakov exponent here, and you'll see that it has this property where mu b goes like 1 over b star. This just simply becomes 1 over b. And you can put in the next to leading order expressions for gamma k and gamma PDF, and you'll see that this thing would generate a very large log. And in fact, the W term will vanish as a 0 if you explore this. So to protect yourself against this, this is recognized back in 1979 by Parisi, Petranzia, Altarelli, Bazzi, Catani, Lori, and so forth. They used a method of adding 1 to these large logs so that they would vanish when you go outside the design region of where the W term applies. We introduced similar device, which where we introduced not only do we have a large B boundary condition, but we have a small b boundary condition. So we define this BC of BT, where when BT goes to 0, you have this minimum value that's allowed. It's equivalent to adding 1 here. So essentially our logs are, excuse me, log of q squared b squared plus some constant that's dimensionless. All right, so so what happens is our mu b star then comes to be mu bar, where we've just replaced b star with b star bc of bt. Okay, we back when we were writing our Bessel paper, we even encountered this issue where we recognized that we needed a b min and a b max, but it was a bunch of ignorant people not reading the literature at the time, because this was already established before. Okay, so just to keep you alive and thinking, here's my W new, as in where I still have this OPE piece, and I have this non-contribution. And all I've done here is replace B star with BC of B star of BT. So you can think of this as just 2 boundary conditions. We had one for B max, now we have for B min. So this is what people were doing, but we tried to, we did this maybe a little more organized manner. So what happens is the W term for the unpolarized now is a function not of B, but BC of BT. The Sivers first moment is now a function of BC of BT. So, and the unpolarized, TMD, and the Sivers TMD just have this substitution. Okay, so the form is exactly the same. Now, interestingly, what happens is that if you look at the correlator, remember I said that it's the correlator that undergoes CSS evolution. Well, if you throw this into the correlator, you're going to get two terms that have two different spin structures. And the coefficients of the functions are what evolve, but this BT that's sitting here in the correlator does not, because it's on either side of the equation. And so it's just this scalar function that evolves. So we don't lose the symmetry or azimuthal, cylindrical properties of the correlator. So we do not replace there. Yes. Yeah, sure.
And this replacement BC to BC, you are doing it also in the non-perturbative
Yes.
part.
Very accepted. Yes.
Is it important?
Oh,
Is it crucial or,
yeah. So it could give rise to power correction. So that's not part of my talk. We can talk about it, but for sure there are power corrections that would appear up there. In other words, if you we can talk about it later, but it's kind of a diversion. But it might be a device to study power correction. Yeah, numerical. I don't know. Maybe ask Ted and the Blue. I haven't done anything with just conceptual about that.
meaning principle, you should have enough freedom in the non-perturbative part to avoid, to avoid the need of.
Yeah, I mean, and we've talked about, the different forms for GK to B and so forth. So yeah, it could become part of that, but it also might be interesting if you're looking in the perturbative region. For small b, what is happening, right? There are pieces that are that aren't there in the previous. Okay, so what's very clear once we have kind of fixed up what the Sudakov is at small b, doesn't blow up. It becomes pretty clear that when you look at the small b limit of the Fourier transform TMDs, which is essentially what this equation is, that if the coefficient function is well defined, calculated, the leading order of best functions. So what do you get? You get the Fourier transform function evaluated at B min, but B min is in fact a scale that is related maybe to the normalization scale. We'll say a little bit more about that. So we, at leading order, we get a relationship. But I don't think you should be thinking of this integral here symbolically as integrating over the TMD. What you're doing is you're really looking at the space, looking at the BT goes to 0 with this regularization. Yes, Elka.
I asked a really stupid question from an experimentalist.
Yes, absolutely.
I apologize in advance.
Yeah.
Wouldn't all be much easier to do it in PT space?
No. No, because of, I'm not saying you can't. I'm not saying you can't, because you can do TMD evolution in PT space.
No, you can't.
Excuse me? You cannot?
You cannot.
Well, I don't want to say, that's also another discussion. There are people.
The answer for that and not so.
No, there's not a.
Experimentalist, so why? Because it's forward and back, it sounds to me.
It's not from up from the speakers or the result in content.
Summarize it into.
Because the evolution depends on here. Then when you put it format, you have some problems. So you cannot put the complete.
No, let's have a discussion later about it.
Okay, over coffee or lunch or wine tonight.
I have something that's slightly new and
it's okay.
maybe a little.
No. Good.
Okay.
I can wait.
Anyway,
At leading law, we definitely can. At leading law, we definitely can do it. And PT space is intuitively more appropriate because you know what's perturbative, what's not perturbative in PT space, but it's not in the sec. Then Chris Lee at Los Alamos actually is working exactly on this, working in PT space directly. In South Carolina takes Fury, by the way. So I think it's not totally irrelevant. So the question whether it can be done consistently in this space is interesting. It is difficult, and it's known since 80s, as you said, that it's difficult beyond the world. But intuitively, I think it's more appropriate because we measure everything in this space. After all, come on.
Let's finish.
Let me finish. So the other thing I want to point out is, and which is I think a little more important, is that since we know the evolution kernel for the Sivers first moment, we know that the statement that was written in the paper by John Way, Mert, John Collins, Ted, has a collinear limit. And this is a well-defined quantity. So when people write KT perp over 2m squared symbolically integrating this, what they really mean is that they've done this from B space, and then it's well-defined. Okay, now the question is, what about next to leading order? Yeah, I'm almost done. So the way we did this was to look at the coefficient functions. So let me go back a slide that I should have repeated here at this point. So imagine you're looking here, and you're taking the small b limit, and it turns out that the exponent is well behaved. It goes to something that doesn't blow up because we have the b min. We have what Katani did, but Werner did this as well. We're going to look at coefficient function as bt goes to 0, but with this replacement of b star, bc, and bt. Okay, so the way you calculate the coefficient function, so we're doing it next to leading order, excuse me, we're not doing all orders here. So the way you do this is just look in the appendix of Ted's paper, Mert, or else look in John's book. The coefficient function is this product becomes, you do a next to leading order expansion, you get the coefficient function at 0th order, which is 1, times the collinear PDF. And here you have the first order TMD and B space. And so you have to calculate a bunch of diagrams. The result is well known. It's been known for 7 years now in the formalism that John developed. So here is the coefficient function for the quark into a quark. And you have this expression. Point to note is that you're canceling the collinear divergence here that exists in the collinear PDF and also exists in the TMD and B space. So all you're doing, the only difference between these two objects is you're given e to the I kt integrated over kt when you do the integral. Rather here, you just have, you can think of it as integral over kt. So you have to calculate these diagrams. You can do it in many forms. Ignazio's got a form for this in different scheme and so forth. Yeah, I know. I'm just trying to demonstrate something simple, which is the next to leading order correction to the statement that we had that the leading order, we can relate leading order collinear. So the soft functions are right plus soft functions. Right? They're there. Okay? So I'm not going to go through the details, but what we get is exactly the MS bar representation with the splitting function here times the log of q squared over uf without the 1 over epsilon because the 1 over epsilon is canceled in the coefficient function. So this 1 over epsilon is quote unquote when people say they absorb it into the bare PDF, which is problematic. We essentially get that result plus finite terms depending on what scheme you use. Okay, so in 2014, Werner doing joint resummation also canceled the collinear divergence and subtracted it, I should say, and got an expression that I didn't have time to put in here. Maybe he can talk about it, but essentially what it is f at n, 0 for b at x is some initial scale times e to the I splitting function, where if you did that to first order, you would get the same result. So what I want to say is that you can use the B-space formalism to connect, not get, but connect these pictures. That's what I want to say. If you do a different scheme, you'll get your coefficient function here can actually just be this term right there, 1 minus x. So That just means it's evolved to a different scale. All right. And in fact, if you look in the paper of Elena and Alexei, you'll see the evaluation of this quantity here at the scale then where these logs cancel. Where, for example, you let, okay, I don't want to go into that. There are different schemes for this. Anyway, so we can get we can connect the collinear PDFs to the moments of TMDs in the OPE picture. So I think it's somewhat dangerous. I should have put this slide. Yeah, and also there's this paper by Ignacio and Vladimirov about, I think, looking at twist-3 objects in a similar fashion, which haven't penetrated. But let me go back to my first slide and ask people if they think that this is an accurate thing to have in the white paper, because the impression that people get is that you can do an integral over the TMD and get a collinear PDF, and I think that that is, as Davidson Soper knows well, and others, is fraught with difficulty, and I think it needs to be elucidated anyway, and I'm open to, should this be changed? Anyway, so that's the last thing. I had one more slide. I wanted to point out that we also showed that the cross-section, at least the W term, factorizes. This was done in the earlier paper with Ted and other than Ted and everybody. And then we also did this in this newer paper for the Sivers, where we actually have TF times T1. Okay? And then you want to do higher order corrections. I'm going to preempt a question that Ted won't ask because he's too polite, but he always asks us, what are the power corrections here? And we actually have something to say about it, but I won't say it here. Daniel came up with some kind of interesting discussion on that. There's much more I could say, but here are my comments, and I'll quit.